Hello, friends. I'm Ashish Darbari, founder and CEO of Aximize. To our new listeners, welcome, and to our old ones, welcome back. And I'm very happy to say today I have in house Daniel Zimmerman, a scientist working at Galva Incorporated. Hi, Daniel. How are you?
I'm fine, thanks.
Hey, thanks very much for coming in today, Daniel. Just start right away. So, tell me a little bit about your journey. How did you actually end up in Galva, and what is your personal story?
So I grew up in the late 70s and early 80s, and I got interested in computers at a very young age. My first computer was a Commodore VIC-20, and I would program it by typing in programs from magazines. And so I knew fairly early on that I really wanted to work with computers. But I had no idea that there was such a thing as computer science,
Yes.
right? And it wasn't really until I got to university that I actually was exposed to sort of the mathematics and the scientific principles behind how these magical devices actually worked.
Sure.
And then I knew I really wanted to work with that as opposed to just, programming for a living. And so I did my undergraduate and graduate work at Caltech. And as an undergraduate, I was exposed to all sorts of interesting things, hardware design, distributed systems, software design. I ended up focusing on distributed systems in grad school, but with a formal methods sort of bent, where I worked on, how do we reason about distributed systems that can change over time. And then from there, after grad school, I ended up teaching at a couple different places for a while. I was at the University of Washington for a bit and Harvey Mudd College for a bit, teaching software engineering and formal methods and computer science theory. And then from there, I learned about Galois, which is a whole company that is built around the ideas of formal methods and the application of formal methods to trustworthy computing. And I got hooked, basically.
So Dan, you had quite an incredible journey. So you pursued computer science right from the days of being a hobby to then having a university degree, then getting an interest in formal methods. But then you actually started teaching in university, which is great. And then you said you wanted to come out of the university environment back into Galva, which I believe is a research institution. Am I right?
Yeah, Galois is, we're mostly a research and development services company. So we do a lot of work on research projects for the US government. We do work with commercial clients on high assurance systems.
Right. So we'll go into more details about what you guys are doing at Galva, but why Galva is called Galva? What is the secret?
So Galois is named after the French mathematician Évariste Galois.
Right.
And he did a number of pretty remarkable things during his short career, which was, cut short by an unfortunate duel. But he, one of the things he did was to come up with the idea of Galois connections, which are used pervasively in our field. And he also made fundamental contributions to cryptography, which was the area that Galois was started to address back in 1999.
Wow. No, very nice. Yeah, I certainly have heard of Galva. I've used Galva connections in my own work. But actually seeing that a whole organization exists as a tribute to Galva is awesome. So give me a high-level overview of the kind of activities you're engaged at Galva. So you're an R&D organization and you're also offering services work and you mentioned that you offer this to private entities as well. But what is your main focus point? Are you looking to develop or are developing formal methods solutions for software or hardware or for everything?
So when Yellow started, it was primarily about software, and even a bit more narrowly, primarily about cryptography.
I see.
Over time, as the company has grown and people with different interests have joined, we've broadened our interests into different areas of software, into hardware.
I see.
And so now, essentially our goal is to advance the cause of trustworthy computing systems, broadly construed, right? Whether that's trustworthy software, trustworthy hardware, hardware-software co-design, verification of existing things, development of new things. We do formal verification of commercial software, for example.
I see.
So if you probably our most visible effort in that regard is the work that we've done for Amazon.
I see.
On their S2N cryptography library, where if you go to GitHub, this is an open source thing that Amazon has, and if you go to GitHub and you look, you will see that they actually run proofs of their code as integration tests effectively every time something is merged into the repository, and we help them develop those basically.
So have you been working with Daniel Kroning's group and Byron Cook and so on, or is it a separate piece of work that's going on between Galva and Amazon?
So I personally have not been involved in the Amazon work. I know that we have worked with both of those individuals.
I see. So it's part of the same project, I suppose.
It's sort of part of the same umbrella.
Awesome. So let's talk about the ninja formal methods. What is ninja formal methods? That's the first time I've heard this phrase.
So it's actually secret ninja formal methods.
Oh, secret. I see. Yes. I missed the secret.
The secret part is important because so secret ninja formal methods was a idea that my colleague Joe Canary and I came up with back in around 2008 when we were both teaching undergraduates and graduate students software engineering.
I see.
And the idea is that we know that we can make more reliable software systems by using formal methods and formal methods tools, but the learning curve to actually do those things is very high. And students, especially in undergraduate early days where they want to learn how to build nifty software systems, but they don't really want to spend a lot of their time learning the math and the theory behind what makes a reliable software system. So secret ninja formal methods is the idea that we can take the power of formal methods and package it up in ways that allow non-experts to use it without having to know that it's there.
Right. Just to see the value of it without actually making them do the work in the first place.
Exactly. So we have, principles for how to make, in this case, software sort of verifiable more easily. Different design patterns and ways of building things. And so we teach people those, and we show them that, if you do these things and you're using, the big integrated development environment that we've supplied you with at the beginning of the semester, for instance, then you basically get continuous feedback about how good your software is.
Right.
And not just here are bugs that appear on these lines of code, but also here are things that are logically wrong with your, right? It doesn't satisfy this particular condition. And so the idea then is essentially hiding the math inside user-friendly tools so that people who know how to program or know how to design things and are used to working in IDEs or the like, can pick them up and use them without having to be formal methods experts.
And this is a great way, because otherwise they're used to testing. Everybody knows that you have to test a program, whether they're writing a bubble sort program or they're building a chip. Everybody knows they have to do testing. But to try and make them see that there is another way of looking at verification via a proof-centric approach, this is a great idea. In fact, one thing that I find common with how we're approaching this in the context of RISC-V is through an app which we give to the users to use it without them needing to know any formal methods necessarily. So this is a great idea. So is the secret, now the secret is out, Secret Ninja formal methods, is it actually constantly deployed in your environments at Galva? Is it something is still pervasively used?
So we use, in some of our projects, we definitely use this methodology. It's less a specific set of tools and more a methodology, right? Because Secret Ninja formal methods for hardware is going to look a lot different than Secret Ninja formal methods for Java or for Rust or for C.
Correct.
And so we do use this methodology, at least on the projects that I have been involved with. And, we do know that other people use it for teaching and in various other places. One that you mentioned that was interesting was testing. This helps with testing too.
Correct.
Because typically in a testing environment, you're going to be handwriting a bunch of tests and you're obviously going to miss things.
Of course.
But in an environment where you have these sorts of specifications of your code, a lot of the tests that you would have written by hand can just be generated for you.
Right.
And so we do that too, right? You press a button and now you actually have a full test suite for your program that you didn't have to lift a finger to write.
Yeah,
other than pressing that button.
I can totally believe that. So in fact, a lot of the work you're doing in Galva is in building tools, isn't it? Whether it's for software or for hardware verification, but the whole program is build tools. And are these tools, presumably you're selling these tools, with the licensing model to your customers. And how are they compared to those tools being sold by the commercial EDA vendors, Cadence, Mentor Graphics, they're called Siemens now, Synopsys, OneSpin?
So I will say most of our projects do end up involving the development of some tooling. And Galois has several sort of flagship tools that we have been developing since our inception. One of those is called Kryptol. And Kryptol was originally developed as a domain-specific language for cryptography.
Right.
Where it was Galois' first project, basically, and it is our most mature tool. But it's evolved over time, so it's not just a language. So it's a functional language. It looks like many other functional languages for specifying cryptographic algorithms. But it also has, a strong type system that helps you get everything correct. It also has, a built-in randomized tester to do fuzz testing and the like.
Right.
It also has interfaces to automated solvers for proving theorems about your cryptographic algorithms.
So let me just briefly stop you. So this kind of a tool is not made by the commercial EDA vendors, right? So are you deliberately keeping a differentiation in Galvas to not actively compete with the vendors, or what's the plan?
So the other thing that I'll say is that Kryptol and its accompanying tools, when they were developed primarily for the purposes of software specification and software verification.
Right.
We've recently started using them more for hardware-related projects. And you're right, they are very different than the sorts of things that are offered by the big three EDA tool vendors. And I think that it is probably to our benefit to keep them different because, very honestly, they have resources that we do not, right? We develop these tools in the service of whatever research we're doing for our clients. And most of them are open source.
I see.
Right. Kryptol is open source. SAW, which is the software analysis workbench, which is essentially it's our main verification tool and allows us to do things like equivalence checking between Kryptol specifications and programs in C or other high-level languages or LLVM bytecode. These things are open source.
Okay.
And we make them available to whoever wants to use them. On the hardware side, we're still developing our capabilities in this regard.
Right.
So, one thing that I'm hoping that we'll be able to do in the not too distant future is prove the equivalence directly between Kryptol specifications and system Verilog RTL. Right? It's not clear exactly what we're going to do in terms of a licensing model for that sort of capability.
Sure.
Because the hardware space is a bit different than the software space in that regard.
Sure. And actually, the solver technology under the hood, especially with SMT solvers, looks very different. If you were looking to do word level solving for hardware, I don't know if the SMT solvers are ready for that kind of analysis for hardware. I think for software, they're much better suited. Or at least that used to be the case some years ago. So tell me a little bit more about Kryptol. Is this the thing that you deployed at the Amazon project?
So Kryptol is definitely one of the tools that we used with Amazon. We also used SAW, as I mentioned, the software analysis workbench.
Right.
So I'm not sure what do you want to know about?
So what I wanted to know was that, supposing you have a software house that is designing some software, presumably with some hardware that they may or may not own. I mean, should they come and talk to you and look at your solutions? I mean, is there a prescribed flow that you suggest to your customers who are new to using formal or formal-based flows?
Well, I would definitely encourage them to come talk to us about it. We're always happy to talk to people about how to best improve the assurance stories around their software and their hardware, or both at the same time.
Right.
There are, of course, things like tutorials. As with any tooling that people make available, we have tutorials for how to get started with Kryptol and how to get started with SAW. We've been working more recently on sort of teaching materials related to these things that will eventually be available in some public way.
I see. Okay, that sounds good. So what I was actually looking to find out was, I was reading up some of your stuff, and there was an example you gave about what happens when random number generation goes wrong. And I think do you want to share a bit about that? Because there's a lot of random number generation going on in UVM test bench environments, automatically done. I wouldn't say totally automatically done, but it's done for simulation purposes. So what's the big deal about random number generation?
So I think random number generation is essential to many cryptographic algorithms security, right? In terms of generating keys. If you have a bad source of randomness, then somebody can reverse engineer how you generated your keys and then break all of your cryptography. Even if your cryptographic circuits are perfect, even if you're using everything correctly, if you don't have good random number generation, then you're going to be using weak keys, basically. And then all of the perfect cryptography in the world isn't going to help you. that actually is an area where Kryptol and SAW, can help. But, true random number generation is the kind of thing that really ends up having to be done in hardware with, various methods of having randomness in physical hardware. And for that, I think, formal verification of that is not something that we've really done a lot of work on. But some of the ways that random number generation has failed in practice in the real world are definitely things that you could catch with verification tools. Probably my favorite example is back when Sony released the PlayStation 3. They had this, really high standard cryptographic ecosystem around it for signing software distributions and making sure that nobody could install unauthorized software on their consoles. And it turns out that the random numbers that they were using for signing key generation actually weren't random.
I see.
It turned out that they were using fixed numbers. And so once somebody reverse engineered what those fixed numbers were, they were able to just distribute arbitrary software. And Sony couldn't plug that hole because, it was already out there in the world. They couldn't change their whole cryptographic scheme. They would break millions of consoles.
And this would affect everything that runs around, our satellite TV subscriptions. I mean, pretty much the, Netflix subscriptions, whatnot. And what you're saying is you guys have been working on some solutions, if not all the solutions that we need.
Well, I would say that the things we've been working on. So, if you were to run verification tools on the software that generated those bad Sony random numbers, you would pretty quickly find out that they weren't random.
Right. Okay.
But I don't. That's not that particular issue. Isn't one that we've spent a lot of time looking at explicitly. Things that we have spent more time on is, are the actual cryptographic primitives and protocols implemented properly?
Right.
Because a lot of mistakes get made there as well. Good cryptography is hard, which is why it's pretty universally suggested that people not implement their own.
Yeah. So this but
somebody has to.
Yeah. I mean, one is the protocol aspect and the other is, as you said, the random number generation side, where coming up with a formal proof that a given software's random number generation algorithm is robust, I think would be very difficult.
It would be.
But at least you can find holes and you can find bugs and defects. That's something that is possible today with the technology you're building. That's quite useful to know. Because, we can't solve all the world's problems. We've got to solve the ones that we can.
Right. So, now, the ones that we can solve, that we have done in previous projects, are things like, how do you go directly from a mathematical specification of a cryptographic primitive to hardware, to a circuit?
Nice.
And so we have a tool flow that goes from Kryptol to actually system Verilog.
I see.
That we can use to generate correct by construction sort of golden models for circuits that you would then implement on actual chips. And then you can have very high assurance that your cryptographic circuits are correct.
Right.
Of course, if you feed bad data into them, like bad keys and bad randomness, you're still going to get bad data out, but you've eliminated at least one possible.
How would we ensure that the compiler is correct? The ones that spit out system Verilog from Kryptol?
So that is actually a good question. Right now, we have done that by checking the resulting system Verilog against sort of reference models that are known to be correct. In the future, we're hoping to actually be able to use our equivalence checking tools to check the system Verilog directly against the Kryptol that it came from, so that you don't have to actually trust the compiler as long as you can prove the correctness of what came out of it. Developing an actual verified compiler from Kryptol to
would be
hardware
hard.
would be very hard.
That would be hard. I mean, you could do that in a theorem prover, but that is not what I was after. What I was thinking you could do, I don't know if you do already, is to extract human readable specifications from Kryptol models and turn them into assertions that could be exercised as protocol checks on your system Verilog design model. That way you get a nice sanity check to see if the certain sanity properties are not failing on your extracted code.
Indeed, that's also something that we've considered doing, and I would love to get the opportunity to do as part of one of our upcoming projects.
I mean, this is the main problem, isn't it? When we are doing high-level synthesis, and this is an example of a high-level synthesis in that sense. People think of System C, but this is a classic example of high-level synthesis. And we're always wondering, now we trust the compiler. Okay, we are more willing to trust the compiler than the human beings, but the compilers can have bugs too. No, but that's very interesting to know. Okay, Dan, so tell me a little bit more about some of the hardware projects that you're working on.
So at Galois, as I mentioned, we kind of pivoted a little bit into hardware several years ago. And mostly we've been doing projects in hardware cryptography, as true to our roots. One of those, the first one that we did was called GULPOC, which stands for Galois Ultra Low Power High Assurance Asynchronous Cryptography. One of the other things that we do is asynchronous logic, and the combination of that and correct by construction is pretty powerful. In that case, we implemented a number of different cryptographic primitives, taped out an ASIC, used Kryptol to actually do the high-level specification of the cryptography, and compiled it down to system Verilog, and got really good results in terms of not just the correctness, but also the performance that we ended up getting out of it, and the power utilization. Coming out of that, we did a project which we just recently got the chips back for, and haven't had a chance to analyze yet, called 21st Century Cryptography, where we did some more correct by construction cryptographic accelerators, in particular for AES 256 and SHA.
Right.
And in this case, not only did we synthesize them from Kryptol, but we also did some interesting side channel resistance things on the chip to try to see how we could leverage asynchronous design to improve security, in addition to improving power and performance.
I see. So that is ongoing work, or is it completed work?
So that work is mostly completed, but the analysis of the chips is ongoing.
Right.
So, we've done simulations and the like that tell us certain things that we think we can expect about the side channel resistance of the chips we get back. And we just have to see how that actually turns out in silicon. And then we just started a project about a month ago, which is called Basilisk. And that project is to develop a hardware accelerator to accelerate fully homomorphic encryption.
I see.
I am not sure if that's a term you or your listeners are familiar with.
I was just going to ask you, what would that mean in more simple terms?
So put simply, fully homomorphic encryption basically is computation on encrypted data. The idea is if you wanted to do some really high-powered computation on a data set, so maybe you want to do it in the cloud, in somebody's cloud environment, but you don't trust them with the data, right? What you can do if you had a solution for fully homomorphic encryption at speed is you could encrypt the data before sending it up to the cloud, send it up to the cloud, do whatever computations and processing needed to be done on it while leaving it encrypted the entire time, and then download the results and decrypt them.
Wow.
So essentially,
that sounds
you don't have to worry.
Yeah, sounds impossible.
Well, it's not impossible, but it's very, very hard.
Right.
So typically, fully homomorphic solutions that exist today are mostly in software, and there are some FPGA accelerated things that are in research labs, but they are many orders of magnitude slower than just computing on unencrypted data. And so it's not really practical to do these computations at scale.
Right.
The goal of this project is to develop a hardware accelerator that will bring the execution time of these things down to within a factor of 10 of computing on unencrypted data, so that it'll be a bit slow but quite practical.
Wow. Sounds really, really nice and quite novel.
Yeah, it's an exciting project. That project is for DARPA as part of a program that they have called Data Protection in Virtual Environments.
I see.
And we're really excited about it.
Yeah, so that really sounds quite exciting and out of the world. Hey, we've already spent half an hour talking, and I didn't realize the clock was ticking. We've covered a lot of ground today, Dan, and I think we should do some deep dive again in a follow-on chat. But I would like to wrap up for today in the interest of time. I know you're quite busy. But one thing I want to ask you before I let you go, we have a lot of listeners who are in 20s and 30s age group, so I would say relatively young career professionals and students. And I'm always asking my guests to give us a few tips for students around the world. If they were looking to pursue a career in formal methods, I know that Secret Ninja would be one way of going about it. But tell me, in your view, having taught in universities before and working in corporate environments, what would be some of the tips that you would like to give?
So first, I'll say I would certainly be happy to come back and do a deep dive on any of these topics.
Let's do that, yeah.
We should definitely do that. As far as a career in formal methods, I think partially that depends on what we mean when we say that. In terms of using formal methods and trying to improve whatever it is that we're doing by leveraging the power of these things. I think that there is a lot of very approachable tooling out there these days, right? Even things like SMT solvers, that used to be much more difficult to use than they are now. If you're interested in learning about how these things work, it's fairly straightforward to just grab one off the internet, right? Grab a copy of C3 and work through some examples and just, get a sense for what these tools can do, what they can't do. For people who are interested in working behind the scenes and improving the state of the art, clearly a lot of the mathematical experience is going to be necessary. But pretty much every university now has courses related to these things. So I would think, just exploring, you take a tool or a concept that resonates with you and, download it, play with it, look at its source code if it's open source. Most of them are, because this is a very sort of open and welcoming community. And talk to people. Those of us who have been thinking about this stuff and working with this stuff for a long time are, I think, on the whole, really excited about the fact that the use of formal methods in industry has been accelerating rapidly over the last,
Indeed.
even just the last 3 or 4 years.
Yep.
With companies like Amazon doing formal methods in the open on some of their higher profile software tools. So there's a lot of opportunity out there, and I think we tend to be pretty approachable people.
Cool. I think what you're saying is get your hands dirty, go out there on the GitHub, grab the tools, and talk to people, which is, I think, is quite reasonable. Awesome.
Yeah.
So,
and if this is an area that you're interested in, we do internships at Galois. We're always ready to, have people come and work with us as well.
Of course. So that's good. I mean, I presume you're based in Oregon. So are you a US-based entity only, or are you spread around the world?
So we are a US-based entity only. We have 3 offices. Our largest is in Portland.
Right.
We also have offices in Arlington, Virginia, and Dayton, Ohio.
Okay.
Although right now, because of obviously the COVID-19 situation, everybody is remote.
Working from home, yeah. So, well, anyway, so you have US work rights and you're interested in pursuing a career in what I certainly believe is one of the best disciplines. It's the most happening thing. Then, get in touch with Galois and work on all of these exciting projects that Dan was talking to us about. Hey, thank you very much for your time today. I really appreciate you taking time off. I know you've been very busy. We were trying to schedule this for a couple of months, but I'm glad we could find time to talk about it. And I'm looking forward to welcoming you back, Dan.
I'm looking forward to that as well. Thanks.
Thank you. So, friends, I hope you liked today's chat. If you certainly are feeling as inspired as I am, then get in touch with us at info@axiomize.com. Look up Dan Zimmerman's work at Galois. And talk to us. As Dan said, we are lovely people and we are very approachable people. And with that, we'll wish you well and we'll be back shortly.